You may or may not have heard of the widespread tale that Archimedes realized how to detect whether a crown is made of pure gold when he was taking a bath. This story is often related with the so-called Archimedes principle. Archimedes' principle states the buoyant force Fb on an object equals the weight of the fluid WFL displaced by the object, while the buoyant force is the net upward force on any object in any fluid, due to the fact that the pressure increases with depth in a fluid, so that the upward force on the bottom of an object would be greater than the downward force on the top of the object. Archimedes' principle is valid in general for any object in any fluid, whether partially or totally submerged. Let's look at this example together. To solve for the buoyant force, we need to find out the weight of water the object displaced. And basically, it depends on the volume of the water it displaced. In part A, because the solid steel is completely submerged, the volume of water displaced equals to the volume of the solid steel itself, which is 1.28 times 10 to the 3 cubic meter. So that according to Archimedes' principle, the buoyant force equals to the weight of water displaced, that is density times volume times g, and we get 1.3 times 10 to the 7 Newton. Please note that this force is smaller than the weight of the solid steel, so that the solid steel remains completely submerged. In part B, when the volume of water that is displaced increases to 1.00 times 10 to the 5 cubic meter, the buoyant force also increases and becomes 9.8 times 10 to the 8 Newton. This means that if an object can displace more water, it will experience a greater buoyant force. Density plays a crucial role in Archimedes' principle. The average density of an object is what ultimately determines whether it floats. If the object's average density is less than that of the surrounding fluid, it will float. Otherwise, an object denser than the fluid will sink. If an object does float, the extent to which a floating object is submerged depends on how the object's density is related to that of the fluid. Since the object is floating, we have the buoyant force equals to the weight of the object. And according to Archimedes' principle, the buoyant force should equal to the weight of the fluid that is displaced by the object, so that we have the weight of the fluid displaced equals to the weight of the object. And we can see that equation is simply rho fluid V fluid equals to the average density of object times volume of the object. We can thus define a term called fraction submerged equals to the submerged volume to the volume of the object. And because the volume submerged equals to the volume of the fluid displaced, we have fraction submerged equals to the volume of fluid displaced over the volume of the object. And combined with this equation, that is exactly the average density of the object over the density of fluid. We usually define specific gravity as the ratio of the average density of an object to the density of water at 4 degrees Celsius. This is a dimensionless quantity. If an object floats in water, its specific gravity is less than 1. If it sinks, its specific gravity is greater than 1. Let's look at this example together. Since the woman floats, her average density should be smaller than the density of water. We know that the fraction submerged equals to the average density of the object over the density of the fluid, so that we can calculate the woman's average density to be the fraction submerged, which is 97%, times the density of the water, and we get 970 kilogram per cubic meter. An alternative approach of using the Archimedes principle is shown in this figure. An object, here a coin, is weighed in air and then weighed again when submerged in a fluid. The density of the coin can be calculated if the fluid density is known. On the other hand, the density of the fluid can be calculated if the density of the coin is known. Archimedes' principle states that the buoyant force on the object equals to the weight of the fluid displaced. This in turn means that the object appears to weigh less when submerged in the fluid. We call this measurement the object's apparent weight. The object suffers apparent weight loss, which equal to the weight of the fluid displaced. Alternatively, on balances that measure mass, the object suffers an apparent mass loss, which equals the mass of the fluid displaced. Let's see this example together. We are given the coin's mass, so we just need its volume in order to calculate its density. Since the coin is submerged, the coin's volume equals to the volume of the water displaced, which equals to the mass of the water displaced over the density of water. We have known that based on Archimedes' principle, the mass of the water displaced equals to the apparent mass loss when the coin is submerged into the water, and that is 0.83 gram. So that the volume of the water displaced is 0.83 cubic centimeter, which is also the volume of the coin. Please note that here it is convenient to keep the units in gram and centimeter instead of using kilogram or meter. Finally, the density of the coin is the mass divided by volume, which is 10.4 gram per cubic centimeter. In the widespread tale, it is believed that Archimedes used the exactly same method to determine the density of the crown to see whether it is made of pure gold. Have you ever seen some insects walking on water instead of floating in it, or a needle rests on a water surface? Both these cases here are related to an effect called surface tension. To understand surface tension better, we need to know that there are attractive forces between water molecules. These attractive forces between molecules of the same type are called cohesive forces. Then, when cohesive forces between molecules cause the surface of a liquid, say the water, to contract to the smallest possible surface area, this effect is called surface tension. Surface tension is the reason why liquid form bubbles and droplets. The pressure inside the bubble is greatest when the bubble is the smallest. You may be able to confirm this if you have ever blown a small balloon yourself. The balloon is super hard to blow at the beginning, but once the air starts to fill in it, it gets bigger very fast if you keep the same effort of blowing. Besides cohesive forces, there is another type of attractive forces, which are the attractive forces between molecules of different types, and they are called adhesive forces. Why is it that the water beads up on a waxed car but does not on bare paint? The answer is that the adhesive forces between water and wax are much smaller than those between water and paint. The angle theta between the tangent of the liquid surface and the surface of the other material is called contact angle. And this angle is directly related to the relative strength of cohesive and adhesive forces. The larger the strength of the cohesive forces within the liquid relative to the adhesive forces between the liquid and the other material, the larger the contact angle would be. And it is more easier for the liquid to tend to form a droplet. The same is true when the liquid is in a narrow tube or capillary tube. The tendency of a fluid to be raised or suppressed in a narrow tube or capillary tube is called capillary action. If a capillary tube is placed vertically into a liquid, capillary action will raise or suppress the liquid inside the tube, depending on the combination of substances. Mercury is suppressed in glass tube because its contact angle is greater than 90 degrees. Surface tension exerts a downward force, suppressing it in the tube. The dashed line here shows the shape of the mercury surface would have without the flattening effect of the surface tension. On the other hand, water is raised in a glass tube because its contact angle is nearly 0 degree. Surface tension therefore exerts an upward force when it flattens the surface to reduce its area. We have skipped all the calculations in this section. You may read extra materials in the textbook if you are interested. There are pressures in various parts of our human body. For example, blood pressure, pressure in our eyes, and pressure associated with the lungs. There are also bladder pressure, stomach pressure, and pressure in the middle ear. All of them can provide valuable medical indicators for our health. You may read the textbook to gain a general understanding about how the concepts of pressure we have learned can be applied to all these real-life examples.